We are going to resume the mode of operation for different type of reactor. For a batch, it's closed and it's in dynamic mode of operation. A fed batch is semi-opened and it works in a dynamic mode. Only the substrate could be constant for the fed batch. Continuous Stirred reactor it's an open reactor and it functions at a steady state. And plug flow reactor, there is two ways to look at it. If you look at the entire reactor, it is open and it works at a steady state. But if you look at a slice of volume dV, it is closed and in a dynamic mode. Dynamic means that parameters are variables. We are going now to explain how to make a global balance material on a reactor. We will say first that accumulation is equal to entrance minus exit. This is the sentences we will use all the time to make a global balance. We will use the indice I for in and O for out, exit, in, entrance. Let's see how we will do a mass global balance. We will write that accumulation is dm on dt, derivative m dot I is the flow mass at the entrance minus m dot O is the mass flow at the output. We can replace m, the quantity inside of the reactor, by rho times V, and m dot I we can replace it by rho times Qi. Because m it's rho times V and m dot I, for example, at the entrance, it's rho times Qi. You can check all that with dimension of each terms. As rho is constant during the time, we can take it off the term of accumulation, and we will have a simplification of all the rho in the equation. So we will have at the end dV on dt is equal to Qi minus Qo. It is a volumetric balance. So we can change a mass global balance in a volumetric global balance. In a global balance, we are speaking about all the flow and all the volume, the material inside of the reactor . We are going to give some global balance for different type of reactors. So, for a batch, for a fed batch, and for a CSTR. Let's see. For a batch, we know that there is no flow. Qi and Qo are equal to 0. So dV over dt is equal to 0. when a derivative is equal to 0, that means that V is equal to constant. It's a constant. The volume doesn't vary in a batch. In a fed batch, there is an input flow. So dV over dt is equal to Q in. And we will see in some examples that we could do the derivative, the integration of this kind of equation. For a CST air, dV over dt is equal to Q in minus Q out. And because they are equal, Q in is equal to Q out, dV over dt will be equal to 0. That means that the volume is constant. As for the batch, it is constant. We are going to make now a balance on an element of the reaction, because we are speaking about bioreactors, so we have some elements in reaction. We will call it I. Accumulation of I is equal to entrance of I minus exit of I plus production of I, if we have production of I, minus consumption of I, if we have consumption of I. It will depend of the element, or it is a product, or it is a consumption, or it is a substrate and it is consumed. So we will use these methods to make a balance on an element, on a bioreactor. Let's see an example with a balance, a material balance, a mass balance on a product. On a product, we will call it P, the concentration of the product, it's P. So, accumulation of P, it's dmP over dt. Variation of mass of P during the time. It's the mass flow of P at the entrance minus the mass flow of P at the output. As it is a product, we will say plus R triple prime P time V. I explain this expression. M dot P I and M dot P O, O for output, I for input, are the mass flow of P. Mass flow at the entrance, at the input, and mass flow at the output of the reactor. Mass flow of P, of the element P. The unit could be gram per hour, for example, because it's a mass flow. R triple prime P, it's the rate of production of P. It's a volumetric rate, so the unit is gram per liter per hour. That's why we have to multiply it by V in the equation to be homogeneous in the equation. All the terms are in gram per hour, for example. I explain what is a mass flow of P at the entrance. A mass flow of P, it's the concentration of P at the entrance time the volumetric flow at the entrance. If we look at the unit for this expression, a mass flow is gram per hour, for example, concentration is gram per liter, and the flow, volumetric flow, is liter per hour. Qi, it's a volumetric flow. mP, the mass of P inside of the reactor, is the concentration inside of the reactor times the volume. So we can change the expression in dCP times V over dt is equal to Cpi times Qi for the entrance minus Cpo times Qo for the output plus the rate of production of P times V. Say Cpi, it's the concentration of P in the input flow, and Cpo for out, O for outflow, output flow is the concentration in the output flow. A balanced material on an element is useful to describe what happened inside of a bioreactor and to predict the volume or the concentrations, a lot of parameters during the bioreaction.